All right, let me tell you a technical horror story. It's about a really common piece of code, something tons of developers use every single day. But it has this hidden flaw. A flaw is so dangerous it can lead to total data corruption. And yeah, even serious financial loss. So this is the result. This is what happens when everything goes wrong. A user, let's call her Alice, just managed to withdraw money that she doesn't actually have. Her account is now sitting at a negative balance. She literally just stole $100 from a fintech service. And what's truly terrifying? She could do it again and again and again. So how is this even possible, right? How does a totally standard function of withdrawal become a tool for a heist? Okay, let's dive into it. It all comes down to a classic programming problem that gets a deadly new twist in the world of modern cloud apps. Here's the crime, broken down step by step. So Alice, she sends 2 withdrawal requests for $100 at the exact same time. Request A hits one of your servers and reads her balance. $100. Simple enough. But before it can save the new balance, request B hits a different server and also reads her balance. And guess what? It still sees $100. Now, request A finally finishes its job, sets the balance to 0. But a moment later, request B, which still thinks the balance was 100, also subtracts 100 and saves. The final balance is now negative $100. Ouch. You know, if you were running this on a single old-school server, a monolith, this is a solved problem. Piece of cake. You just use a simple lock or a synchronized block. The operating system itself acts as a single, trustworthy referee for all the different threads. But we live in a distributed world now. Our servers, they don't share memory. A lock on server 1 is completely invisible to server 2. So we need an external referee. We need what's called a distributed lock. And this brings us to the big dilemma. If our application servers can't be the referee, who can? We need to find some kind of central shared service that all our other servers can talk to, to ask for permission before they touch something important like Alice's bank balance. So let's take a look at the usual suspects. These are pretty much the main contestants. You've got tools like Zookeeper or ECTD, which are built from the ground up for correctness and consistency. I mean, these are the heavyweight champions of safety. Then you've got your reliable old databases like Postgres or MySQL, which have locking mechanisms built right in. And then you have Redis. It's known for being super fast, simple, and most importantly, it's often already part of your tech stack for caching. So it's the popular choice. But is it the right one? So because Redis is so common, it's the tool that most developers reach for first. I mean, if you Google distributed lock, you're going to find countless tutorials pointing you to a simple Redis command. It seems elegant, it seems efficient, and it seems so easy. But this is where our horror story takes a very dark turn. The popular suspect has a secret. And this right here, this is the key piece of evidence. This single line of code is the most common Redis Lock implementation you will find anywhere online. It looks so simple, right? You just set a key, but only if it doesn't already exist, and you give it an expiration time. Let's break down what it's actually doing. The first key part of this command is that NX option. This is the heart of the lock. It stands for set if not exists, and it's an atomic command. That just means Redis guarantees it'll either succeed or fail as a single unbreakable operation. So if you send this command and the key isn't there, Redis creates it, and boom, you've got the lock. If another process already holds that key, the command fails, and you know you have to wait. It seems totally foolproof. Okay, the next part is PX 30,000. This sets an expiration time on the key. In this case, 30 seconds. And this seems like a brilliant safety feature. I mean, after all, what happens if your client gets the lock and then just crashes? Without this expiration, that lock would be held forever, and the whole system would grind to a halt. So this time to live, or TTL, it's our safety net. But what if I told you that this very safety net is what's going to cause our entire system to fail? And here's the twist. That safety feature, it creates a new, much more subtle and, honestly, a terrifying vulnerability. It's called the zombie process problem. It comes from a scenario that in the Java world is known as the garbage collection horror scenario. And it proves that what you think is a dead process might just be sleeping. Let's walk through the timeline of this disaster. At time 0, client A gets the lock. It has a 30-second TTL. It starts its work. But then, at the 5-second mark, client A's process just freezes. Maybe it's a stop-the-world garbage collection pause or a temporary network lag. Could be anything. While it's frozen, time just keeps kicking. At 30 seconds, Redis sees the lock has expired and deletes the key. At 31 seconds, client B comes along, asks for the lock, and Redis says, sure, go ahead, and grants it. Client B does its work, writes to the database. But then, at 45 seconds, client A wakes up. It has no idea that 40 seconds have passed in the real world. As far as it's concerned, it still holds the lock, and it proceeds to write its own changes to the database. And boom, that's data corruption. The crucial point here is that our lock completely failed. Client A, the zombie process, had no idea its lock had expired. It woke up and just overwrote the valid work done by client B, leaving the database in this inconsistent, corrupted state. The very thing we built the lock to prevent has just happened. So this reveals the fundamental flaw. This simple Redis lock is built on a really dangerous assumption. It's basically a lie. It assumes that if a client is silent for 30 seconds, it must be dead. But in a distributed system, silence doesn't equal death. It could just be a really long pause. And when that process comes back to life, it can cause absolute havoc. Now look, this is a deep and a hotly debated topic. Even the creator of Redis proposed a more complex algorithm called Redis Lock to solve this, but other experts, like Martin Kleppmann, have argued that it's also fundamentally flawed. So in a future explainer, we could totally dive into that debate, talk about when Redis might still be okay, and look closer at the safer alternatives like Zookeeper and Postgres. But for now, we're left with this really unsettling question. This whole problem, it happened because our lock relied on the simple passage of time. But in a world of distributed systems, with all their network delays and process pauses, time itself becomes, well, unreliable. So if you can't trust time, what can you really trust?